Randy mentioned some of his technical difficulties, but he actually also alluded to the technical difficulties in the theory front. He mentioned that after so many years, we still don't know whether Hubble model really supports single connectivity. And the reason is for these quantum many-body systems, in particular, when the interaction is strong, we really do not have a good, reliable theoretical tool to handle these things. There are very precious few exactly solvable quantum many-body systems, but most of the systems cannot be solved exactly. So you have to rely on some approximate method. And one commonly used approximate method is in the framework of perturbation theory. You have some small parameters, you can do perturbation to different orders. But when the interaction between a particle is strong, perturbation really does not work. There is no small parameter that you can use to do the perturbative expansion. So for these type of systems, we need to come up with some clever approximation, and we need to justify these approximations. But it's not always the case. And another way to do is just to brute forcefully expand the Hamiltonian into some basis and then try to diagonalize the Hamiltonian. But for many-body systems, the Hilbert space is huge, and we cannot simulate the system using our classical computers in an efficient way. So before until a real quantum computer can be constructed, we really face this great challenge that we do not have a good handle on many of these quantum many-body systems where interaction is strong. And that unfortunately is also where the system becomes more interesting when interaction becomes larger and larger.
Okay.
I have a question about the Rydberg atoms. So if you keep an atom in, say, n equals 300 state, and you're basically seeing the electron particle moving around in circles around.
If you engineer it correctly.
Yeah.
If it's in a stationary state, it will be a stationary state.
Exactly. So, but if it is a stationary state, and you basically then you have a wave packet that is so confined, you basically have a charged particle moving around in a stationary state, but it wouldn't radiate like a classical particle moving around in circles, so that it loses its energy. Because if it's in a stationary state, it has the same energy all the time.
Well, but this is a superposition of different stationary states. The way you make a wave packet is you'll take a small mix of, say, n equals 301, 302, 303, and 304 states. Mm-hmm. So they're all superposed, and they'll stay localized for a while, but unless you work really hard, they won't stay localized for too long, because each of those states evolves at a different rate. So the wave packet tends to spread out around the world.
But there's another answer to your question. It's a very interesting question, because if you're in a high L state as well, so that there's only one decay channel out of n equals 300. Let's say you're in n equals 300, L equals 299. Then it has to go down to n equals 299, L equals 298. That's the only place it can decay to. It turns out that if you do a classical calculation of what the radiation rate is classically for something in that radius orbit, that lifetime is exactly equal to the quantum mechanical lifetime of this decaying spontaneously from 300 to 299 to within some fraction of a percent. Mm-hmm. So it's a really nice correspondence between classical and quantum physics.
So there was a mention of quantum computing, and I was wondering what would need to happen for quantum computing to take off. Like what needs to be, what components need to be in place, and is that 10 years from now, or is that 50 years?
Well, there are actually some applications of, I'll say, more general quantum information science that are here today. There are, it's not the desktop quantum computer, but this general field of putting information in quantum mechanical objects and taking advantage of that quantum mechanical properties to do things with information that you couldn't do otherwise. That's actually here. You can send information on light fields through fibers very, very safely. And there are actually products that people can buy that you cannot eavesdrop on this fiber. So that That actually exists. Now, the bigger goal is to actually have a register, and you can do real calculations that you could never do on a real computer, and that's a ways away. Right now, I think people have gotten up to 8 quantum bits, and we're still putting together the pieces essentially. Because 8 quantum bits, it's amazing, it's fantastic what they can do, but yeah, you need to do something realistic. You have to worry. You have to be able to have a lot more information in there. Maybe hundreds of bits. You have to solve problems of decoherence and the fidelity, the accuracy of the measurements that aren't there yet. I think the greatest experts in the field, the ones I respect the most, are the ones that are the most conservative also. They're like, it's a long ways away. There are a lot of big questions. Will we be able to scale up our little thing to something that actually can survive? We don't know. But on the other hand, there are lots of people working on it. It's very, very exciting. And there are lots of different technologies, so no one knows which technology will be the best one. There are things in atoms. It's been major contributions in the field have come from work with atoms. But solid state systems are also have proposals that can do this kind of stuff. A lot of work has been done, and everything now in a computer is done in silicon. So there's an inertia, there's a comfort level in doing something in a solid state system as opposed to having lasers and atoms. That's a very different kind of computer than somehow doing it on a chip. So there's a lot of work that will be done. I don't think anybody's going to be buying quantum computers for decades. But I do think more and more applications will come out as these systems become more robust, they're able to do more things, and as I said, there already are some applications already.
Microsoft funds the Q station at UC Santa Barbara that is dedicated to quantum computing. So they're putting real money in it.
So Han, earlier you kind of mentioned about the synergy between theory and experiment. And I was wondering if you guys could comment more on kind of how in AMO physics specifically theory and experiment complement each other. Does one need the other, or how does it generally work?
Yeah, so, well, I said that in particular in AMO physics, theory and experiment go step sometimes. Experiment leads theory, sometimes the other way around. And for instance, in this quantum degenerate gas in 1995, 3 groups realized boson can condensate in neutral atoms in one Randy's lab, and so those experiments certainly stimulated a lot of theoretical interest. So the field just exploded, and there are tons of theory papers on quantum degenerate gas. And another recent example is again in Randy's group, and also in the MIT group, we created this 2-component Fermi gas, but the 2 components have different population. So there is some many decades ago, in the 60s, people studied this problem in a theoretical way. What happens is in superconductors, you have a different, you have Z-band field that breaks the degeneracy between spin up and the spin down electrons. If the Fermi levels are different for these different spins, how do they pair up to form Kummer pairs? And what is the nature of the superconductor? And will this destroy the superconductor completely, or will there some kind of exotic superconductor will come out of the system? Okay. But it turns out that to realize this in solid state material in superconductors, it's really difficult. But in atomic physics, you can do this relatively easily. You can independently control the population in different spin species, and this is what we did in the lab. And that again stimulated hundreds, if not thousands, theory papers. So that is another way, another example where experimental groups leads the theory. But there are also numerous examples where a theory serves as a guidance to the experiment.
I think quantum computing is definitely the latter. All the proposals for quantum computing have been out there for a long time, and theorists identified the potential, and even I think they have identified all the different architectures that could work, and then experiment. They're tough experiments. Some of the experiments that take years to finally get there where they're starting to put these pieces together.
I have a question for Dr. Dunning. You alluded to a couple of quantum mechanical behaviors, such as the decoherence of information because of the different time evolutions and superposition of states. And Dr. Hewlett discussed sort of regimes where you see a convergence between classical and quantum behavior. Do you see any purely classical elements of your Rydberg atoms?
In many respects, they do behave classically, but if you start looking for things like coherence, and you still see that even at n equals 300 or n equals 600. I mean, you will see revivals, which are, you've got a wave packet that has many components. As time goes by, they get out of phase. Now, if they retain their coherence, if you wait long enough, you'll get a revival. They'll all move back into phase. And then you get a revival. You see another feature, and then it decays away and comes back. And if that is lost, if you don't see those revivals, then you know you've got decoherence. So you've lost the information that you've got. You can store information in a wave packet, remember, by either the phase of the individual components or their amplitudes. If you lose the phase information, you've lost the information. And you can recover the phase information and reconstruct a wave packet by doing, if you take data for a long time, you do time-domain Fourier transform spectroscopy, and you can get not just the amplitude of the Fourier components, which correspond to the different ends, the different rotation rates, but you can get their relative phases. So then you know the components and their phases. You can construct the wave packet. So you can actually put information in either the phases or the amplitudes, and you can get that back later and get the whole, recreate the whole wave packet. Years ago, somebody wrote, I can't remember what it was something like AMO physics in an atom, and constructed the wave function you would require that would actually do that. Have a probability density that basically said AMO physics.
What about chaotic dynamics? Barry, this is like another example where chaos and quantum mechanics come together, classical physics and quantum physics.
That's correct. You can do that in the same thing. If you go out to late times and high driving frequencies, then you'll get chaotic, it should be chaotic behavior. But if you look, phase space, okay. If you look in phase space, you can imagine certain classical orbits, okay, where it might be a period 5 orbit. If I kick it just at the right 5 times, it's going to go up a couple of n, come back a couple of n, and end up where it starts. The problem with that is that you have to kick it precisely at the right time. So it's actually not stable, because you just simply cannot achieve that. But quantum mechanically, if you look at the wave functions for the evolving system, there is a wave function in phase space that actually sort of knows about this. You will get regions in phase space where you say, God, oh, that looks awfully like that period 5 orbit. And it's a wave function, and it's stable. And you can actually load those, and we've managed to do that. So we've actually loaded states which classically would not be stable. But quantum mechanically, it sort of knows that. The quantum mechanics somehow knows that there is an underlying classical physics and sort of produces wave functions that look like it. If you look at the stadium, which is a well-known problem, which is kind of an oval, like a dog track, with 2 ends, and you look at how particles might bounce around in that, that's chaotic. But if you actually look at the wave function of the system, you'll see hints of what the kind of classical orbits that go kind of this way, that. You can just see hints of it in the wave packets and the wave functions.
What do you use to provide the kicks to the
A very short electric field pulse, usually about 600 picoseconds long. Remember, the orbital period for an atom at n equals 300 is about 5 nanoseconds. So you can sort of sit there and watch it go around with modern electronics. And then you can give a very short electric field pulse, which just delivers an impulsive kick. So we kick the atoms into shape and we manipulate them with kicks.
And the observation, how exactly are you observing them?
We can either observe the n distribution, or how many we've got of what n. We can observe the evolution of the x coordinate, or the y coordinate, or the z coordinate.
But in more detail, I mean, what physical quantity are you measuring?
Survival probabilities. We give them a kick, and we see where
remaining.
How many remaining. Or you can do Fourier analysis.
And you apply for the tear of the electron off.
Ultimately, you knock the electron off, yes.
And then the number is measured by fluorescence of atoms.
We count the particles. I mean, we're working, I mean, you've heard from people here about the ultra-cold, ultra-low energy, ultra-low temperature. In a sense, we are working in the ultra-intense, ultra-fast regime. Because for an atom at n equals 300, an electric field of 1 volt per centimeter is more than enough to tear it apart. It's ultra-intense, much bigger than the field the electron experiences from the core.